Last unit, integration and indefinite integral, A, B, C, D, E. Really, D and E are where we're hopefully going, but if I think you need A, B, and C to understand what's going on with DE. Integration is a second component of calculus. It's really closely linked to differentiation, but where differentiation, you find the slope at a point, the slope of the tangent at a point. Integration, you're finding the area under the curve, essentially. Now, how it's linked to differentiation and how you find it and why you'd find it, I want to make that clear in this set. It's a little bit long, but I don't know, maybe go take a break, intermission, get some popcorn. We're going to start by looking at the area under the curves using velocity time graph. So this is velocity, 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 and this is time, 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 meters per second and seconds. Think about this. This is like your toy car is moving at 5 meters per second, right? This is its velocity. So its velocity is constant for 10 seconds, right? The velocity is increasing, so it's going slower, 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 and increases for 10 seconds. And this increases quickly and then kind of tapers off the acceleration up to 10 seconds. Let's just look at this piece. This means your car is moving at 5 meters per second. That's a 5. Sorry, this part of it. This velocity is 5 meters per second, 1 second. Oh, I should have picked a different number than 5. And this piece, this width, is 1 second elapsing, right? You chem nerds, the seconds and seconds cancel, and you're left with just the distance, right? Because velocity times distance, velocity times time should give you distance, physics nerds. So this area is the distance that it's traveled. It's traveled 5 meters in that time, right? And here's another one, right? We're going for another second, another 1 second, and its velocity here is the same, 5 meters per second, just like this one. So this was 1, 2, 3, 4, 5. It's moved 5 meters. This one, 1, 2, 3, 4, 5 more meters, because we've been traveling 5 meters per second for 2 seconds, right? So this is, you can think about it as 5 meters per second per 1 second, right? For 2 seconds. Seconds cancel, and you get 5 times 2 is 10, and just meters. If you did that for all of them, or for the whole shebang, right? You said, hey, look, I'm moving at 5 meters per second for 10 seconds. That gives you the area here. That whole area is 50. And if you counted these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you'd get 50 squares. Yeah? That area under this curve represents the distance traveled if you're talking about velocity and time. Is that okay? If you're not a physics nerd, you should be. It's fun. All right, so, and that's how I see integration first and foremost, and then I apply it. So let's try this. Get out of here. I want to do the same sort of thing, but with this graph, right? Now, I could kind of count up these half squares, right? This is easy. Count up the squares if you want, or just go length times width. This is the same sort of thing, but you can like add up the little squares, or you could use some basic geometry. Somebody use some basic geometry, which is the area of a triangle is what, 1/2 base times height, right? And this base is 10, so we get half times 10, and the height. So this is 10. This is 5. 5. It should be 25. It should be half of this one. So the area here is 25. We were talking about the base is in seconds, the height is in meters per second, the seconds cancel, and so we're just left with meters, right? So great, I can do this one with like basic geometry, this one with basic geometry. This one's harder to do in 10 seconds. Yeah, I could see this is like 1, 2, 3, 4. We count up these, count up these, count up these, add up the little pieces. But it's maybe not as complete as if there's as if it's an easier line. So when you have these interesting curves, we need a different tool, and that tool is called integration. I know you're excited, so let's check it out. You could use it also here, like if you were looking at how much force a rocket motor puts on an object over time. This is easy to calculate. This is easy to calculate. And so if you said, all right, well, force is in kilogram, it's in newtons, right? Which is a kilogram times meter per second squared, right? If you take that, that's what this height is, right? If you take that, and if you, I don't know, we could maybe make a little rectangle out of it. The height here is the force, and if you multiply by the distance over, you'd get time in seconds. Seconds and seconds would cancel, and you're left with kilogram times meters second, right? You're left with kilograms times meters per second. Physics nerds, momentum. And if you knew the mass of something, you could just plug in the mass. Oh, wrong one. Plug in the mass, and you could find the speed. So if you knew the area under the curve, you could figure out the velocity. Likewise on, this is a cumulative frequency graph. This is the, I don't know, like the height of a sunflower, right? And you have 8 sunflowers that are 20 centimeters high and 5 flowers that are 15 centimeters high and 15 flowers that are 25 centimeters high. And if you added up all of these, right, if you found the area underneath this, this would be the number of the occurrences times the length, right? And so this number would just multiply by the length, and you get like total length of all the sunflowers that had been grown stacked end to end. Yeah. Why do you want to do that? I don't know. Bragging rights. I grew more sunflowers than you, right? So the area under the curve generally has some interesting meaning. Sometimes it has no meaning, but generally it's interesting. So let's figure out how to calculate it without counting stuff. Move your face. Gee, move your face. All right. So here's a curve. We want to find the area underneath it. Unfortunately, it's curvy, as curves are. One way we could do this is, instead of calling this like a curved surface, we could kind of approximate it by putting in little rectangles, right? And I know that I'm missing this space here and this space here and this space here, but like sometimes we don't have any other option. So let's just envision it as little rectangles, right? We're going to call them the lower rectangles because we're using the lower corner of the rectangle, right, to approximate that. And we could say, well, the area of the rectangle is 1 unit. Each one is 1 unit wide. This is the change in x. I'm going to call it delta x, or maybe dx. So this is the dx, right? The change in x, the dx. And so is this, and so is this, right? And the rectangle's area is the height at that point, right? F of 1. We put in 1. We put 1 into here. You get 1 squared is 1 plus 1 is 2. That's where this 2 comes from. And so this is 2, right? So distance over times distance up. Add that to the next rectangle. Distance over, also 1. Distance up is f of 2, which is f of 2 is 5. So we got plug 2 in there, you go 4 plus 1, that's where they get this 5. So this area is 1 times 5, right? And you could keep doing that as far out as you want it to go, or had time or patience. You could also maybe take the, not the lower boundaries, here, let me pull this out here, but the upper boundaries, yeah? And so the upper boundaries would look like this. We're using this side and drawing the rectangle here like that, and drawing this rectangle here. That's, so one is undershooting because we're missing some. One's overshooting because we have too much, but they kind of approximate, right? And you could play the same game with this. You could call this, you could say the upper boundaries are still, sorry about the mess, dx, right, change in x, times the height, and then you just add up the areas. Okay? Hopefully that's not too bad. Now, this is pretty awful with all of this. Let me get rid of this stuff. This is pretty awful with all of this, all the squares and like the big chunks missing. But what if you make this smaller, like this, right? We could approximate this curve with 1, 2, 3, 4, 5 big chunky blocks, and you'd have a lot extra there, there, there. You'd have a big chunk missing there and there. If we made them smaller, instead of making 5, maybe if we made 10, now we only have a little bit hanging over here, right? Now we are only missing a little bit there. And if we make our change in x, our dx, if we make that even smaller, we make 20 little spaces, right? Now I can't really see how much we're missing. Here, we're still missing chunks. Here, missing less, right? We're more closely approximating this curve. And as this change in x, or our dx, remember in differentiation we called it h, as that dx approaches 0, we're going to get closer and closer to the actual integration, the area under this curve. We're back to using limits, and that's why this is calculus. This is why it ties into the derivatives, and we'll get there in a second. All right, that's the whole idea. Make rectangles, make as many of them as you can, and they approximate the area under the curve. Add them up. Okay. Put myself back in order. We can talk about a definite integral. We'll do this a little later. Definite integral means I have spots to start and stop. Indefinite integral means I want all of it ad infinitum, the whole area. But the whole thing remains the same. We're going to take each of these widths. That's our, what are they calling it here? W. They're calling it W. There it is, width. Right? This is kind of, you don't have to worry about the nuances here, but W is the width of our chunks. They're all the same. Instead of W, I'd like to have you think about it as change in x, or dx. Right? So there's width, width, width. Notice it's in all of them because you have to go length times width. That length for each one is the height. Right? You get the height from f of x at that point. Okay. So this is the definite integral. We write it like this. We go from the lower limit to the upper limit. We're going to work with indefinite integrals first, so don't worry too much about that. And the integral finds you the area under the curve. This big notation like that is an S for sum. You're summing up the areas of these little rectangles, right? So it looks scary, but it just means add up all of the areas. You sum them from one limit to the other. It might be going from 0 to infinity, right? I want a theoretical idea about how big it is in total, but sum them up. You're going to use whatever f of x they give you. Maybe you're going to use, I don't know, 3x squared plus 2, and your graph is going to look like this, right? Right? And you'd be summing all the areas underneath. There's a fast way to do this, and that's where we're going. All right. So I want to show you the trick to make this work. So let's go back to that beginning chunk. This is constant velocity, 5 meters per second for 10 seconds. This is our f of x, right? The equation for this line is y equals 5. Instead of calling it y, I'm going to call it f of x equals 5. All right. Therefore, the area, if we were just going to talk about this area under the curve, right? The area should be the integral from 0 to whatever x we're going to use of that f of x, the function f of x. Now, you should have no idea how to find this, but the nomenclature, the writing of it should make sense, hopefully now. Area is going to be the sum of all the boxes and each one is f of x tall, and d of x wide, right? Length times width. F of x is 5, I just substituted that in, right? So each one's 5 tall, and each one is d of x wide, however many we want to break that up into. Now, we said this was length times width, right? Here's length, there's width, and length times width here was 5x. Right, 5 is the height, and x is the distance out. And I'm not sure how big that is, right? We could break it up into tiny, tiny pieces or big pieces. I'm not sure. But I wanted you to see this component, right? We're going to do this twice. Here's f of x, here's a of x. And I want you to think about how we go from here to here. Yeah? Let's do it with this one. F of x is half x, right? Half x because it starts at 0. This is plus 0. This is just the equation for this line, right? It's plus 0 because it starts here at 0. It's a half x because it rises 1, runs 2. Rises 1, runs 2. It's just the slope of a line. Nothing fancy here. All right? So this line is y equals 1 half x plus 0. If we were trying to find the area under this curve, the area would be, oh, go away. The area would be the integral of f of x dx. F of x just means, why can't I delete those? There we go. F of x just means the height based on where it is on the line, and dx just means the distance over, right? We're making a little box, length times width, and we're summing them all up. So let's keep going with that, right? F of x was half x, there it is. Dx is still dx, so this is how you find the height. We said really this was 1 half base times height. All right, and I know that this half is here, This is the base. Let's call it that. Sorry, I'm crossing my streams. And this height, x, is just the f of x, right? So 1 half base times height. This kind of got us a little confused, right? But the area of a triangle is 1 half base times height, right? Okay, so if we rearrange that a little bit, you get the halves come together to give you a fourth, the x's come together to give you x squared. So this is what we ended up with. My original function was 1 half x. When we took the integral, we found the integral of it was 1/4 x squared. Similarly, previously we had this 5 as our function, and 5x was our area under the curve. If you look at these with your nerd goggles on, you'll realize that if you had a function y was 5x, if we started with this, right? If you found y prime, if you found the derivative, you get 5. And same thing, if we started with this and you said y was 1/4 x squared and you took the derivative, y prime, you'd get 2 times a fourth, which is a half, and then you decrease the exponent by 1. You get this. So to go from here, from f of x, to find the area under the curve, we have to do the derivative backwards, right? The derivative of this, the derivative of the area is the line itself. The derivative of the area is the line itself. So if we know the line, to find the area, we undo the derivative. We do anti-differentiation, which is taking the integral. Soak that in. Soak it in. All right. So this is kind of a synopsis. The integral is the area under the curve. You find it by taking the antiderivative, by underiving. That's the theory behind it. We'll figure out how to do all the chunks. That's a big jump. There's a lot of math to prove this. I showed you 2 examples and hoped that you made the connection. But I think that the math behind it is interesting, but it's not necessarily worth our time at this moment. So, just as a synopsis, if you know this curve equation, right, if you underive it, if you think about the equation that would give you this as its derivative, that'll give you the area under the curve. I know that's the first time you've seen integration, so let's try one. All right, let's just do the mechanics. I want to find the antiderivative of x cubed. All right, well, the antiderivative means I'm going backwards. I want to take some function. I want to take, I don't know, some function, f of x, y equals f of x. And I want to take y prime, take the derivative, and end up with x cubed. Well, there's only a few things that this could be, because I know that we'd start with this. I know when we take the derivative, if we started with some a term, x to the some n term, I know that this is going to go from n down to 3. We always decrease by 3. So what is n going to have to be? I don't know why I'm asking you. You can't respond to me. N's going to have to be 4, right? Because when we take the derivative of this, this decreases by 1 and you get 3. No problem. The problem is that if you just were differentiating x to the 4th, if you're trying to find the derivative, if y was x to the 4th and you're trying to find the derivative, you'd say, okay, 4 multiplies in the front and then drops by this, right? Well, here I don't see a 4 in front, right? I'm expecting a 4, but I don't see a 4. I see a 1 there. So that means that there had to be something in front that canceled out with this 4 to give you a 1. So I had to go 4 times something, I'm going to call it a, 4 times something, and it gave me 1. What is the a going to be? A is going to have to be the reciprocal of that exponent, right? If you're not sure what that, so 1/4. If you're not sure about that, you can think about just doing this. If we started with, let's start with y equals 1/4 x to the 4th, and we're trying to take the derivative of it. You'd say 4 times a 4th give you 4 times a 4th. There's your x, and then you decrease this by 1. The 4 and the 4th cancel out, give you 1, and you're just left with x cubed, which is what we want. So this is the derivative. We want to take the antiderivative, which is just going backwards. So increase by 1, and in front is the reciprocal of the new exponent. All right, so let's try C. C, this is ugly, so let's change it over into a different format. So the negative means that this has come up to the numerator, and the half is from this radical. Fine. I know we're trying to take the antiderivative of this, and so, excuse me, if you thought about this in terms of a x to the n, I know that the n would have to, if we were taking the derivative, the n would decrease by 1. So therefore, our n would be 1 larger than 1/2. Negative 1/2, sorry. So positive 1/2. Fine. Also, you'd multiply the half into the front. So you would expect to see a 1/2 right here. We don't. We see a 1 right there. So that means the reciprocal of a half was in front. 2, right? The reciprocal of a half is 2. That means that if you were taking the derivative of this, you'd say 1/2, you'd multiply by the 2 in front, that gives you 1, and then you decrease this by 1 to give you -1. So there's the result we're looking for, right? So this, if we take the derivative of this, we get this, right? So we're working backwards. We want to take the antiderivative of this, so we should get that. Yeah. And so therefore, let's turn this into let's turn this back into a different format. So this is 2 times root x. That's this piece. Yeah. If you're moving through this fast, you could think about this. If you're saying, I want the integral of x to the negative a half, I usually think about dx. You got to leave the dx. It's just the format. You could say, all right, I know that this has to increase by 1, so 1/2, and I need the reciprocal of the new exponent in front. The reciprocal is 2, right? And so this is this.